Okay, I'll try to keep this as brief and painless as possible. But like I said, we're going to talk about energy transfer, and you guys have probably heard of all three processes before. So I just want to give enough introduction that you can understand some of the activities we have planned for Wednesday's class. So as I've written here, energy transfer is we can transfer heat or thermal energy from object to object or from place to place via three different processes: convection, conduction, and radiation. And often there's more than one acting at one time. So, for example, when you're cooking something, it could be two of the three are happening at the same time, even all three of the three. But I just want to give some basic vocabulary so it makes sense to you so that when we're doing activities in class, you'll connect the dots. I don't want to show you some slides because I want to have you try to figure some things out in class. So I've sort of skipped over a few slides. So just bear with me. Of course, as usual, you can stop the video and take notes of whatever, any definition, things like that. But over the course of the next 2 days, it should be clear what you need to understand. It is vocab intensive. So the first thing is talking about conduction. And conduction basically means we have something that's hot, we have something that's cold, and these two things are touching each other. And I'll give you a formal definition in a second. So, for example, if you place your hand on a stove, the cold thing in your hand is going to touch the hot thing, the stove, and there will be some sort of transfer of energy from the hot to the cold. Energy will move from one place to another. The key here is conduction. There has to be contact. There's contact taking place. And again, we'll take a look at a couple examples. Now, a classic example was putting a hot poker in a stove. So if you're that type of person near the fireplace or the campfire that you have to be constantly poking it with a poker, the poker is usually made out of a metal, something that obviously doesn't melt or catch fire. The problem is if you leave the poker in the fire too long, the poker will get hot down here and energy will transfer through the poker by contact. It's really going to be by a series of elastic collisions. Hot molecules of metal will bump into cold or slower moving molecules, and the energy will slowly transfer up. And intuitively, if you leave your hand there for 3 hours, eventually your hand's going to get really, really hot. I'll show you a demo in just a second. So the idea is that the molecules inside this poker are in contact with each other in collisions between the molecules. Even though it's a solid, the molecules still shake and they bump into the molecules next to them. So the energy transfers through the rod, and that's conduction. If you do any cooking, you understand this. I do the cooking in my house. I actually enjoy cooking. It's like chemistry. You get to eat the food. Now, this is where people have to be careful. I cook with pans that have metal handles. They do this on purpose so you can take them from the stovetop and actually put them in the oven. They don't want the handle catching fire. The problem is I accidentally touch the handle all the time. My wife actually did this the other day. I took a pan out of the oven, and she didn't realize it was still hot, so she touched it with her hand just for a second. I heard a yelp. So you have to be careful. It's conducting. The hand touches the hot metal, energy is transferred into the hand, and your skin doesn't like that. Hopefully this picture is not a baby getting hurt, actually. Now, what they often do on pans is they put handles of a non-conducting material. They put something like wood, which is a non-conductor or a good insulator. I'll talk about those terms in just a second. So that will keep the pan handle from getting hot, but obviously you can't put this pan in the oven. You can cook on the stove top with it, but you can't put it in the oven because the handle would burst into flames. So stoves, cookware comes with a couple different types of handles based on what you want to do with it. Now, this is one way of looking at it. This is how the AP usually looks at it, is by what we call thermal conductivity. This is a measure of how well a material conducts heat and sometimes electricity. So different materials, as you know, conduct heat at different rates. Some metals are very good at conducting heat, or some materials are very good at conducting heat, and some are not very good. Things that have a high K value are good conductors, or we can say they're poor insulators, and things that have obviously the opposite, things that have a low K value are good insulators and poor conductors. The AP usually talks about conductivity, but sometimes people talk about the opposite, insulating factor. Your house, for example, in the wintertime wants to have a high insulation factor. It just means you don't want to use metal, for example, for insulation in your house. It's a good conductor of heat. So again, you can look at the same concept, just flip-flopped. Okay. Now we're going to do a lab. I don't want to give away too much. The AP loves to have a lab where you actually have to figure out how quickly heat can transfer through something. We're going to do that in class. So I don't want to give away too much. So I'll talk more about this later. This is one of my favorite things. I can't actually do this. The school would fire me. But the idea here is this is a metal rod. It has different metals. It has different materials. I'm holding the handle that has a non-conducting insulating rod. And what I do is I take the 5 kids who scored lowest on the last test, And each kid has to hold on to one of these different rods. Now, this rod might be copper, this is iron, this is aluminum, this is whatever. And you have the kids hold their hands nice and tight on each of these, and then you place a Bunsen burner full blast right in the center. And some metals will conduct the heat very rapidly, so the first kid is going to yelp in pain. The next kid is like, what's the problem? So different metals have different conductors. The school said I can't do this anymore, but I thought it'd be kind of fun to motivate children not to do poorly. I call it conductivity Russian roulette. Okay? So we can't actually do that, but you get the idea. Different metals conduct differently. And we have a way of quantifying that. This is called the K value. And the units, don't worry about too much, but certain things like metals, like aluminum, copper, and iron, it's how many joules per second over a certain distance or a certain temperature. So how quickly the rate of energy transfer, joules per second, how quickly can that energy move through this material? So if I have a chunk of aluminum, it moves relatively quickly. Copper is even better. Copper is even a higher conductivity. The higher the number, the higher the conductivity. And iron is still good. It's not as good. Now, some of you may actually have this at home. I know I have a set of pans at my house that have copper bottoms. And that's not accidental. They put copper in the bottom because copper conducts the heat from the flame through the pan into the food very quickly. So if you want to boil water fast, get a copper bottom pan to conduct that heat through there. So these are good conductors, and generally metals are good conductors of both electricity and of heat. Things that are poor conductors are things like water. Look at the value. It's at less than 1 joule per second. Air is a very poor conductor. This is why sleeping bags work really well when they're puffed up full of air. Air is actually a good insulator. It's a poor conductor. This also has to do with climate. I talked about this in class. Water, Long Island Sound holds on to heat, but it also gives up heat very slowly. So as we head towards winter, the Sound right now, the water in the Sound is probably at 70 degrees right now. And what you'll find is in Connecticut, the water stays in Long Island Sound. That water gives up its heat very slowly. It conducts the heat away very slowly. So Long Island Sound water will stay nice and warm until October, November, even though the land is going to get cold. So in the wintertime, you'll see the land here is like 30, but the water is like 50. And the same thing, the opposite happens in the spring. It takes a long time to heat up the Sound. So if you go to the beach in May, the land is 70, but the water is still back at 50, 60. It takes a long time for that water, because it's a poor conductor, to gain that energy back and to give it up. Okay? So again, metals in general are very good conductors. Other materials like wood and water and air are very poor conductors. So they have low conductivity values. And again, we're going to do a lab on this, so I don't want to give away too much here. We're going to look at the rate of energy transfer in a lab activity. There's a way of talking about energy, which is Q per time. So how quickly does this energy get transferred? Okay, and that's a real AP question. So now you don't need to know this. I just like to mention it. A lot of people, you guys are eventually going to own a house, and obviously you probably live in a house. So your parents are worried about the conductivity rate. They want to have a high R value. R is insulating value. So we want to limit how quickly the heat leaves your house. So we have insulation in your house. If you drive down the road, you'll see this quite often in houses. You can actually see on the roof, is this good or bad? Well, think about it. You got snow on the roof, and the snow is melting, and you can see the joist in the roof of your house on the plywood. You can actually see the joists in here. Melting snow on your roof is not good. That means the heat from inside your house is actually conducting through and actually causing the snow to melt. You don't want the heat from inside your house leaving the house. So people will line the inside of the house with different insulators. They'll use different materials that are very poor conductors, very good insulators. And we actually sell insulation. So most houses in New England have to have like R30, 15 inches of insulation to keep the cold out or the heat in, either way you want to look at it. A lot of houses have 3 or 4, and it's not enough. Your parents are spending a lot of money on keeping your house warm in the winter and cool in the summer. So most good houses have really high, thick layers of R value. R value is insulation value. It's the opposite of conductivity. And your house is built this way. You have wallboard insulation. There's layers of housing. So, some of you are going into civil engineering. Civil engineers and architects have to pay attention to this. They need to have a structure that works architecturally, but they also have to meet code for different towns and make the house so it doesn't leak out air and stuff like that. Here they're saying this: the Pink Panther sells particularly a fiberglass insulation that's in the walls of your house, probably your house at home. behind the wallboard is insulation, and you have different thicknesses of insulation give you certain R values. So again, this is looking at insulation versus conductivity. This is not on the AP. I may do another demo for you. I don't want to give away too much right now, but there's some demos related to conduction. So here's the definition of conduction. If you want to stop the video and write it down. The key thing is heat is transferred by molecular agitation. In other words, these molecules are, these atoms inside this piece of metal, for example, are touching each other. So the heat from the flame agitates a molecule. It shakes back and forth and bumps one next to it. And that one bumps the one next to it and bumps one next to it. So the heat flows from the hot area to the cold area. And after a while, your hand is going to get warm because the molecules are shaking vigorously. So high-speed particles with higher kinetic energy, could be a solid vibrating or could be a gas moving really fast in the room, are going to collide. So we're talking about the momentum transfer again. They're going to transfer in an elastic collision and make the slower particles move faster and therefore heat up. So this conduction process needs contact. There has to be contact. That's the key. Things are touching each other. And again, we'll do a couple labs. Now, you guys may have done this in chemistry. You don't need to write any of this down. There's something called calorimetry, and specific heat actually measures how good of a conductor something is. Specific heat says how much energy is required to transfer heat from one material to another. And I'll show you an example of this, so don't worry about. The basic idea goes like this. And again, you don't need to write this down, but I have a tank of water that's cold. I take a chunk of hot metal, and you may have done this lab in chem. You take a chunk of hot metal. So let's say this is at 0 degrees. And again, you don't need to write down numbers. So if I grab my pen here and I say 0 degrees Celsius, and I got this at 200 degrees Celsius. Well, if I take this chunk of hot metal, and I know how much water and how much metal I have, I can grab this chunk of really hot metal and drop it in. And then never stir to stir up the water. And what's going to happen is that the temperature of the temperature will go up to maybe 75 C, and this will go down to 75 C. So we're going to start with something that's cold and something that's hot, and they're going to reach equilibrium. They're going to reach the same temperature. And there's a formula we can use to calculate this piece of metal, how conductive is it. If it gives up the heat really quickly, we can time this and we say, oh, it gave up heat really quickly. It's a really good conductor. So those conductivity numbers I gave you, those K values, are determined empirically in the lab by doing this process of calorimetry. You may have done this in chemistry, but again, you guys were remote. So I just like to mention this. You do not need to know calorimetry for the AP test. Okay, but it's a classic example of conduction because the metal is touching the water and it's vibrating the water molecules, and they get hotter and the temperature goes up. Okay, so that's conductivity. Now, the second process is convection. And where convection is involved, there's going to be contact, but it's not the same thing. Convection is defined as energy transfer by mass movement. And what that means by mass movement is that lots of stuff moves together, usually air or water. So mass movement of a substance, air or water. And again, we'll take a look at a few examples of this. Now, the classic example here shows a cloud convecting. If you've been to Florida, for example, you know every afternoon there's a big thunderstorm breaks out. Down here on the ground, the air gets heated, and the air will rise because of buoyancy. And as it rises, it will actually, you'll form clouds. You'll get condensation and form clouds, and the clouds eventually start dripping, and it starts raining. So every afternoon in Florida, thunderstorms build up and rain occurs. So this is convection of hot air rising up, cooling down, and giving up to the water. Now, a couple other examples that are kind of really good examples are things called radiators. They're really bad. A radiator in your house, whether it's this type or the baseboard heat in your house, they're really not radiators. They should be called convectionators. So what happens here, if you take a look at the picture on the right-hand side, we run very hot water through the pipe. So many of you probably have this type, but some of you may have forced hot air. So inside this radiator is a hot tube of water running through. And that hot tube of water comes in contact with, so there is some conduction, comes in contact with the air. So the air near the radiator gets hot. And because it's less dense, all this air starts to rise. So we have this mass movement. We actually have currents flowing in your bedroom, and the air rises. So you've heard the phrase, hot air rises. Well, it does that because it's less dense. It's buoyant. So there's a net force upward in this convection. There is conduction to heat the air, but once the air gets hot, it now starts moving. The air literally moves. Now, there probably is some collisions taking place as well. So there's definitely some conduction as well as convection. but the convection is all the air itself moving. So we say the mass movement of this air. So this name of a radiator is really bad. It's not radiating heat, it's convecting heat. It's moving heat up by convection and conduction. And again, if you want to copy down some notes, go ahead. But, if you have that type of radiator in your house, that's what it's doing. And again, so for people who like to have fancy notes, formal notes, it's all here. Basically describes the process. So I can see the AP, and again, I apologize for not saying that, but the AP is going to ask you some questions, and you want to make sure you understand that, hey, hot water running through the pipe, actually that the molecules of hot water and therefore hot metal in the pipe and therefore the air touching it are going to get heating through conduction. They're touching each other. But then this hot air rises to the surface together because it's less dense. That's going to be convection. It's definitely not radiation, so it should not be called a radiator. But again, now you've seen convection if you cook something like spaghetti sauce. You put something on the stove, the flame comes up. After a couple of minutes, the spaghetti sauce or the water starts boiling. That's because we're setting convection. The hot stuff rises because of density, and the cold sinks back in. So if you cook soup or spaghetti on the stove, you see convection. And there are several examples. If you guys studied plate tectonics back in 6th grade, we now know that the plates of the Earth move because hot magma rises to the surface and then pushes out. You get convection currents. So the plates and we'll talk more about this later in magnetism, but this is driven by convection. Okay, so there's a million examples of this energy transfer. Some of you may even have convection ovens at your house. A convection oven is just an oven that has a fan. Hot air rises, the fan blows the hot air back down, or forces it back down, gets reheated, gets pulled back up, gets blown back down. It's good for making cookies and stuff because it keeps the temperature constant. You don't get hot areas and cold areas in the oven. It distributes the heat nicely. That's an artificial process. Radiation is the one that's weird. We'll talk more about this later, so don't worry if you don't fully understand it. We really have to talk about electromagnetic waves. You may have studied that a little bit, Mr. Horgan, back when you did sound in waves. But these are waves that don't require a medium. So, for example, the sun does not conduct heat to you by conduction. You're not touching the sun. The sun also does not heat you by convection. Hot air is not coming from the sun and hitting you. What's happening is that electromagnetic waves in the form of light and different wavelengths are actually propagating through vacuum, empty space. Those waves of sunlight, whatever that means, hit your body and it causes your body and the earth to warm up. This is by a totally different process. And again, it's a complicated process that we'll discuss later in the course. So we have these electric fields and magnetic fields oscillating back and forth with a certain frequency and period and all that stuff. And these waves, like water waves, come from the sun, but they're not physical waves. They're field waves, or waves of field. And again, we'll discuss this in much more detail later. So don't worry about this one. So again, the sun does not, you're not touching the sun, and the sun does not send air to us that carries the energy. It does it by a different process, by light and some other types of processes. Electromagnetic waves, Mr. Horgan may have talked about this. We classify these based on what they are. So radio waves or TV waves are electromagnetic waves. They travel through empty space. Heat is a form of infrared. It travels through empty space. Ultraviolet, gamma, X-ray. These are all waves of light or energy that travel through empty space. Therefore, we call them electromagnetic. And again, we'll discuss these in detail. So if you were to take a chunk of radioactive material and place it on a desk, radioactive material send out things called gamma rays. They send out waves through, could be empty space, and it will actually cause those waves to interact with your body, which may not be good. For example, you go to the dentist's office, the dentist stands behind a cement wall. That's because he's irradiating your body, your mouth, with X-rays. And they're safe in small quantity, but the dentist who does that 10 times, 20 times a day does not want to get those X-rays. So these travel through empty space or through air, but it's not conduction or convection. Again, the sun's a good example. I'm not going to go through all these in detail. There are special cameras that actually detect heat. You can actually have a heat gun. I don't have the heat gun, but I have a thermal thermometer. I can actually tell the heat of things by pointing a laser pointer at you, essentially. And so some things glow red for hot and blue for cold. So the question is this guy holding a Coke or a cup of coffee? No, it must be a Coke because it's cold. It sends out, they assign a color signature to different temperatures. It's kind of cool how it works. So again, the sun sends energy to us via radiation, okay, not by conduction. This was at Yale. The Physics Olympics has been canceled. You guys are going to get ripped off, but every year we take a bunch of kids down to Yale in a non-COVID year, and they actually pull out their infrared camera that detects heat. And so you can see kids' faces are glowing bright because they're warm, but their hair and their shirts and things like that are colder. So you can actually see the people, even if the people leave, you'll actually have a heat signature left behind. So it's kind of cool. If you put your hand down on a surface and take your hand away, the surface will still be warm. So these infrared cameras can actually see the heat. This is how they find people lost in the forest. They can take a camera that's heat seeking. Even at nighttime, they can fly over the helicopter, point the camera down, and they can see the outline of the human body on the ground if the person, of course, is still alive and they're generating heat. So it's kind of a cool thing. Here's a person holding up again. Is it a Coke or is it a cup of coffee? Well, it must be a Coke because it's a Gatorade bottle, I think. So the kid's face is hot and this is cold. It's a form of light is being radiated out. This is showing a reflection. The radiation hits a surface that reflects it. So they're actually it's not a mirror, so it's just a piece of plexiglass. So again, this is the big thing. I probably could have cut to the chase. So conduction, heat transfer due to collisions between particles and material from the hot side to the cold side. Kinetic energy, transferable momentum during collisions. Convection is mass movement, usually air or some liquid like water from warmer to colder due to a density change. And radiation, again, is energy is carried by electromagnetic waves. And again, we will talk about each of these in more detail. I wanted to give you enough information that you could at least start to think about these processes for a couple lab activities we have planned for Wednesday. So please watch this, take a couple notes, make sure it makes sense. And if you have questions, bring them to class. And again, we're going to start with a demo, and then we'll start to figure out a lab to see how that works. Okay, we will knock off there. Thank you very much.